Okay, so I'll start then. Thank you for coming, and thank you for coming to the talk on Zoom as well. So this is a mini course on the so-called Bernoulli property and the K property. And based on the plan, the first thing that we wanted to discuss was sort of like a version of the Ornstein theorem. And I wanted to, before getting into this proof of the theorem, I wanted to give some broad comments. I wanted to make some broad comments just to contextualize why the so-called finitary isomorphisms are somewhat relevant to the situation. So the talk is the Keane-Smorodinsky proof of Ornstein's theorem. Okay, this is readable. So it all starts with the famous isomorphism problem. When are two dynamical systems the same? And classically speaking, there were three different contexts in which people thought of this. And this is, for instance, in the context of Hanmush's book, which is quite old. So you have, let's say, mu f, a bimeasurable transformation of a measurable space that preserves this probability measure, and yet another guy like this, mu g, acting on some other space, and you want to say that these two are equivalent. So the standard way would be to say that there's an x, there's a phi from x to y, such that phi conjugates f and g, and hopefully it's going to preserve the measure as well. So it takes this measure here to this measure there. So this is the strongest, in a sense. So this is the measure theoretical isomorphism. So measure theoretical. The second is you can look at whether or not the two automorphisms induced on the measure algebras are equivalent. So this is sort of the algebraic way. And certainly measure theoretical isomorphism implies isomorphism of Boolean sigma algebra autos. So if I have a set, of course, my transformation f, I can imagine to take it to its preimage. And so this induces an automorphism of the measure algebra of x. And you can say, okay, so is there a similar conjugacy this way? And then the third way was the spectral method, or spectral way. Rather, Koopman, perhaps, is better to say. Are the unitary operators acting on L2 unitarily equivalent? So one of the first major problems in ergodic theory was to be able to distinguish systems even when perhaps they were spectrally isomorphic. So one example for this is that very early on, people realized that any two dynamical systems that are that have countable Lebesgue spectrum are isomorphic, spectrally speaking. Early on, so let's say von Neumann and other people, perhaps, etc., realized if mu f and mu g have countable Lebesgue spectrum, let's not get into what this means, then they are isomorphic. Then they are isomorphic. They are spectrally isomorphic. Exactly. Yeah, they're unitary operators. That is to say, i.e., there is a Hilbert space isomorphism from L2 of x mu to L2 of y nu, such that this equals this. The problem with this, or perhaps the genius of von Neumann, was that he realized, and other people realized, that possibly this is not the end of the story. Because they had this inkling that shift systems have always countable Lebesgue spectrum, but quite possibly they are not quite the same system. So shift full shifts. So full. Let me just write it like this. Full shift systems have countable Lebesgue spectrum, so they are spectrally isomorphic. But it seems like the shift on two symbols with one half measure should not be measure theoretically isomorphic to the one with three symbols and uniform measure. Okay. And indeed, 20 years later, after this theory was established, Kolmogorov was able to come up with an invariant for measure theoretical isomorphism, and that was entropy. Sinai sort of modified it just a little bit, which turned the definition into the definition that we're using pretty much today. So this is the context. Entropy, so Kolmogorov, I guess it's also good to say, Sinai realized there is an invariant, and this is pretty much the only invariant actually. There's an invariant called entropy, for measure theoretical isomorphism. And that invariant associates, for instance, to the shift. So entropy associates to shift on n symbols with uniform probability, the number log n. In particular, the shift on 2 symbols cannot be isomorphic to the shift on 3 symbols. Now, this is sort of where my part of the conversation or the presentation starts. The next question is, whenever you have an invariant, just as in invariant theory, the next question that you ask is it a complete invariant? Let me perhaps write it more explicitly as well. So the definition of entropy that we're going to be using, or the definition of entropy that the expression that the definition of entropy reduces to in our setting is what I was trying to say. So let me set up some notation. Let me take a positive integer, and a underbar is going to denote the set of a elements starting from 0. And let me put x to be the set of all, or rather space of all functions from integers to a. That is to say, this is the bi-infinite sequences using that you can write using the symbols coming from a underbar. And I have a shift operator. If I have a function, you just increase the index by 1. That is to say, if you have a ticker tape like this, so this is the x, this is the 0th coordinate, this is the first coordinate, and so on. The shift takes everything this way. So now the 0th coordinate is x1, now it's x2, and so on. If I have a probability measure on a underbar, then let me define P hat to be the product measure. Certainly this is preserved under my shift. And now we have systems. We have a bunch of systems. And these are the so-called Bernoulli schemes. Okay, so this is the main subject of interest, at least for the purposes of my talks. So I have a shift space, I have the shift transformation, and I have a certain type of invariant probability measure. Of course, these are not the only invariant probability measures on this. For instance, you have measures that are supported on periodic orbits. But this is sort of like a certain class of measures. That you have also Markov measures and so on. We're going to be focusing on this case. So once you have that, the invariant that Kolmogorov and Sinai constructed, entropy, turns out to be this. And I'm using the Gromov notation in a sense. Entropy of this dynamical system with respect to this measure is, and I'm also going to use this notation, h of p, which is the sum over I pi log 1 over pi. It's a finite number, possibly 0. Okay? And indeed, if you have the uniform measure here, this does produce you log n, where n is the cardinality of n. Okay. So now the question is Kolmogorov-Sinai entropy a complete invariant? And of course, as usual in dynamical systems, perhaps it's better to state this question this way. What is the largest collection of dynamical systems for which the Kolmogorov-Sinai entropy is a complete invariant? And indeed, people did this, and now they're called Ornstein systems. Because Ornstein was able to give this rather satisfactory answer, but of course not the end of the story. Ornstein says, for p hat sigma x systems, i.e. for Bernoulli schemes, the answer is yes. That is to say, two Bernoulli schemes are measure theoretically isomorphic if and only if their Kolmogorov-Sinai entropy is equal, is the same. Now, Ornstein actually did this for countable symbols, etc. as well. And you can go beyond Bernoulli. But for the purposes of my talk, we're really focusing on Bernoulli systems, so full shifts on finite many symbols with these types of probability measures, product probability measures. Any questions? Okay. Or maybe I should also mention these Mesharkin and Blum-Hansen examples. And these people were able to construct or were able to realize certain probabilities such that the full shift has the same entropy, but the systems themselves don't seem to be that it's not that clear that they're isomorphic, at least at the first glance. So maybe I should mention one example like that. Mesharkin and Hansen examples. For instance, if you look at this and this, so this gives you a system on 4 symbols. And if you look at this, 4, this gives you a system on, let me use B for the other one, on 5 symbols. Their entropy is the same. But it's not as clear if they're isomorphic, measure theoretically speaking. So this goes back to Mesharkin, and then Blum and Hansen sort of generalized as far as I understand, I wasn't able to look at the original paper because I don't think it is translated. And as far as I know, the Western mathematicians, let's say, only know of this example because of this paper, because in their paper they are mentioning this particular case. So maybe there's a translation though. I don't know. Okay, so it is still, you see, it's relevant. It's like I give you two systems, one on 4 symbols, one on 5 symbols. Their entropy, this number, you just compute it. It's the same. Are they isomorphic? Ornstein says yes, but it's not as clear how to construct it. So I gave you 3 different senses. Let me add a couple more senses, because that's what we're going to be dealing with. Okay. So we have measure theoretical isomorphism. This implies isomorphism on the level, or at the level of Boolean sigma algebras, which in turn implies isomorphism on the level of L2 spaces. We just saw that isomorphism here doesn't always imply this. Now we're going to go a little bit further. We have this invariant entropy, and it is a measure theoretically invariant. In fact, it is an invariant of a much weaker relation, and let me call this being a cofactor. So weak isomorphism. Because fairly early on, Kolmogorov and Sinai realized that if mu g is a factor of mu f, but this map is not necessarily it's not necessarily invertible, you can still talk about their entropies. You can still compare them. So not necessarily invertible. You can still say that the factor system has to have less entropy, which kind of makes sense, because in order to obtain a factor, you're lumping things together. You're losing resolution, which means that your entropy should decrease, possibly. And so, of course, if mu g is a factor of mu f, and vice versa, mu f is a factor of mu g, their entropies would be the same. But people realized, and this did take a while, that two systems being factors of each other in the measurable category or measure theoretical category is not the same thing as there being an isomorphism between them. I think a student of either Ornstein or Rudolph was able to construct examples. This did take a while. So on the other hand, we can also realize that, maybe I should write it here, even though I'm considering these systems as measure theoretical dynamical systems, this shift is defined everywhere. And so I can say perhaps, and indeed it is a homeomorphism. It is a homeomorphism. So perhaps major theoretical isomorphism is, in a sense, asking for, like, so perhaps we can ask for more. That is to say, maybe we can ask for a homeomorphism phi from x to y that conjugates the two systems. Certainly, a homeomorphism, a topological isomorphism would imply major theoretical isomorphism. And let me write it like this. There's going to be another box here.
So when you say homeomorphism, you mean homeomorphism that also maps to store the measure correctly?
Yes. So, yes, exactly. That preserves measures, yes. But even if you don't consider matching the measures, it turns out to be too strong. And I'm going to mention this in a second. And again, if I wanted, I could have said, I'm not even going to worry. I'm not even going to worry about the topological structure. Let me just ask phi to be just the bijection, the real obstruction here that phi is defined everywhere. That is the real obstruction, not that it is a homeomorphism. And this box, I'm going to put something in a second. But these are sort of all these different senses in which I can imagine the two systems to be isomorphic, conjugate to each other. So here is why this is too strong. That's an observation. And that's why we need this box. And I'm going to put here Ash topological. So this is a digraph that I keep using, sort of like an abbreviation for almost everywhere. And it's an Old English letter. It's called Ash. For high-level stuff, it's fairly useful. Observation.
So by this you mean there exists a settable measure for which its conjugacy is considered?
Yes. Let p hat sigma x and q hat sigma y be two Bernoulli schemes. Here, x is on A symbols, and y is on B symbols. Then we have these bijections. Then there are bijections. There are the following bijections, namely, first of all, bijection from A underscore to B underscore. Bijections from X to Y that commute, that is equivariant, if you want. Oh. And homeomorphisms. Okay? Because if I were to have a bijection between the symbols, this certainly defines a bijection between the shift spaces that commute. And indeed, it defines a unique bijection. And that's going to be continuous as well, a continuous inverse. And on the other hand, if you were to have either one of these, you can realize that it would have to send fixed points to fixed points. Well, if it has to send fixed points to fixed points, the fixed points of the first guy is isomorphic or bijective to A underscore, and likewise for the other guy. So this is, in a sense, you can imagine this to be the space of matchings for 0 cocycles of x and 0 cocycles of y. So this is too strong.
What do you mean in the second line? Space of bijections from X to Y?
Yes.
So that's weaker or stronger than the homomorphism?
They're all isomorphic. Bijection that commutes with this is the same thing as a homeomorphism.
The last line implies the second line is easy for me to see, but not the second line. Every homomorphism is a bijection.
Well, going from 2 to 1 is, how is that? Because if you have this, well, just look at the fixed point of. So if you have a bijection, any fixed point of sigma x has to be sent to a fixed point of y. So any bijection here induces a bijection on the sets of fixed points of sigma x and sigma y. Well, the fixed points of sigma x, for instance, is in bijection with a underscore.
But the arrows, yeah. Okay.
Yeah, I mean they're also like they're all bijective. Maybe I shouldn't. They're all the same. All the same sets. The point is that it's not really the homeomorphism. It is the fact that these pi's are defined everywhere. That is the obstruction. So now you're asking for the next best thing. Give yourself a zero measure room. Right? So this clearly is too strong. So ask for this. So you see, in this case, I'm not even asking for the measures to be preserved, but certainly it will be preserved in this case, up to a permutation. So that's why you look at functions that are continuous of a set of zero measure. So the real obstruction is that the conjugacy that we were looking for in the categories that are stronger than measurable are defined everywhere. So definition, let's say x and y be, for simplicity, compact metric spaces. I think there would be enough. Compact metric. So a partially defined function let me also choose measures. A partially defined function phi from x to y is Ash continuous if there is an x naught in x, there is a y naught in y of full measure, each full measure. I'm just going to write it like this. Up to mu, x naught is the same thing as x. Up to nu, y naught is the same thing as y. And phi restricted to its domain inter x naught I don't want to write it like this. Such that phi is defined on this and is continuous, and matches the measures. No, this is just a continuity. Just like in weak equivalence, I'm just first looking at the or asymmetric relation. If I have such a function that has an inverse whose inverse is also Ash continuous, I'm going to call it an Ash homeomorphism. I can erase this. If phi is an Ash is Ash continuous, and has an inverse, that is Ash continuous. Let me just write Ash C0. Then call phi is called an Ash homeomorphism. And just like in the weak equivalence case, it doesn't necessarily mean that if you have an Ash continuous map from one system to another, and vice versa, they have to be Ash isomorphic, Ash topologic isomorphic. But certainly, if you have a homeomorphism that conjugates the systems, you have an Ash homeomorphism, assuming that you have measure preservation. And certainly, if you have an Ash homeomorphism between two systems, they are measure theoretic isomorphic. And in particular, entropy is also an Ash topological isomorphism invariant. And Keane-Smorodinsky was able to prove that indeed, for Bernoulli schemes, it's a complete invariant. Kolmogorov-Sinai entropy is a complete invariant for Bernoulli schemes in the context of Ash topological context of isomorphism. And this is the topic of my talk. Finally, I was able to give it. So any questions so far?
Just have a comment that you can get not almost everywhere topological isomorphism, but a large set of topological isomorphisms that lose them, right? So this
Yes.
lose them to sets of full measure rather than almost full measure.
Yes.
Once you have a measure theoretic isomorphism.
Yes, yes. But this is also sort of like a thing in, for instance, piston theory, the isomorphism that Lucene would produce would be abstract.
Yeah, yeah.
You don't have any control over it. This one is very controlled. It's a very explicit, they're just like stitching the two systems one step at a time. It's very explicit. And it's fairly elementary, the method. And to some extent, it can be generalized as well. But let me just mention a couple of things then, some remarks. This is sort of like the theorem that I'd like to discuss in the rest of this talk and the next two talks probably. So here are some remarks. First of all, the Keane-Smorodinsky proof is fairly elementary. I mean, they're being very smart with how they're doing things. But essentially, all they're using is the standard Shannon, Macmillan, Bryman theorem plus some combinatorics. And there's some associated logistics underneath all this. So let me just write that as well. So that's good compared to Ornstein, whose proof is very involved. But at the same time, this is sort of like a double-edged sword because their method is fairly limited in scope. Compared to, for instance, Ornstein theory, which is sort of like a whole theory that builds these tools called, distinguishes these properties that are checkable for a wide variety of systems, weak Bernoulli property, very weak Bernoulli property, etc. This is fairly limited. People are still trying to generalize this to some extent. Even Rudolph, people like Rudolph, has some work on this, but it is limited in scope, so it's a trade-off. And perhaps it would be good to mention Katok has a survey on entropy theory, 50 years in entropy. He does have some remarks about this. The point is that this Ash homeomorphism, if you want to do it in the smooth category, for instance, it's going to depend on the partition. It's going to be messy. So it's not really sort of like an invariance that would be applicable for broader systems. Whereas Ornstein theory, right, for smooth systems, if you want to show exponential mixing, implies Bernoulli, you just verify weak Bernoulli property, and you're good to go. Of course, in order to do that, you need to be very good, but can be done. Elementary proof, limited in scope. So I'm going to say something else. And on the other hand, of course, compared to Ornstein, it is telling you more. It's telling you something more specific. Specific construction. Specific construction. Construction. Sharper consequence or sharper conclusion. Which is expected, right? It's like if your scope is limited, it is likely that you have more properties, which means that you can say more things. Okay, so these are the three remarks. Any questions? Now, I'd like to mention a couple of things before we wrap up for today. I'd like to mention a couple different characterizations for Ash homeomorphisms in the context of Bernoulli shifts. So in the context of Bernoulli schemes, it just means that essentially your isomorphism is completely determined by what it does finitely many entries, as opposed to looking sort of like the whole shift, which is very similar to how you look at locally constant functions, right? It's like it's the same thing. Locally constant closed cycles, etc. It's the same idea. Yes.
I'm wondering, except for Bernoulli schemes, are there any like completely invariant or dynamic systems already known?
For all dynamical systems?
No, like for a specific dynamic system. Is there any like example of complete invariance? Like
So yeah, for like non-uniformly hyperbolic systems, entropy is also right. But zero entropy is a wild card. You don't get it by much. I mean, you have sort of the opposite with rapid frigidity, right? They're isomorphic and only if they're algebraically isomorphic. So you can actually prove that it's very rare to find invariance for zero entropy world. So this is the tension between the two. The high entropy world is very complex, but there's not very many invariants, whereas the low entropy world has low complexity of the dynamics, but it's very difficult to find invariants in systems.
But in the context of algebraic, you have the spectral tools available to you too. And in a different context, for translations on compact abelian, they have discrete spectrum.
True. But vortical flows, for instance, have become a little different.
Yeah, I understand. But for some algebraic systems, spectral is still sufficient, for instance. But yeah, so the main, I think, push is that even if it's not entropy, it's going to be something like entropy. It's going to be maybe pressure, blah, blah, blah. A couple different things. There, like underneath all this, I think there's a homology theory hiding, because entropy is a homological. It's like a dimension-like thing. Dimension-like things are homological. But it's not quite easy to see what should be the thing.
Are the Zoom participants able to hear our discussion?
They can hear me.
They do, yeah.
Well, yeah, no, I don't. I mean, maybe much more muted. Yeah. Okay. So characterizations. So in the context of I'm not going to write it actually. I'm gonna discuss this characterizations of Ash homeomorphisms next time. The vague idea. So let me just write it like that. For Ash homeos between Bernoulli schemes, think of, let me just write it like that. Think of locally constant. Or you can also write it like this. You can say homeomorphisms that are determined by finite codes. Determined by finitary code. And because of this property, indeed, in this context, people also call it finitary isomorphism. Another word for Ash homeomorphism is finitary isomorphism. Another word is almost topological isomorphism. So let me write that two probably. It's good. Is the same thing. Finitary isomorphism, which is the same thing as almost topological. Perhaps it would be also good to mention whenever you have an whenever you have an Ash homeomorphism that support x naught and y naught, you can make it so that they're residual as well. So not only are these functions, are these homeomorphisms defined on large sets in terms of measure theory, but they're also defined on large sets, on sets that are large in terms of topology. And there's again sort of like an algebraic interpretation of this as well. I'm going to go into this more in detail next time. Let me also briefly mention the outline. And we'll be done for today. So, outline. Step 1, markers. So somehow you look at the probabilities in the two systems, the probability vectors, and you say, okay, I'm just going to look at one of their components that contribute, in a sense, the most to entropy. You say that I'm just going to match them up. So first you have here p hat sigma x, q hat sigma y, and once you have that marker, you define another shift, another Bernoulli scheme by lumping all the other components of the probability vector that contribute to entropy lesser. You lump them up, and that gives you a Bernoulli shift on two symbols that happens to be a common factor. Okay? Second is to say, okay, I match this and this along this guy. So I'm gonna, so you're trying to build your isomorphism like this in a way that is preserving the fibers. And the fibers are what are called fillers. And this you're using, this to handle this, they are defining something called a skeleton. These are essentially binary sequences, binary finite words in two symbols that are of this form. So you have a bunch of kisses and hugs. Okay, so this part, for instance, corresponds to the marker, and just like, you know, this sort of like reminds me of genes and all that stuff. So you have sort of like a large number of markers that tell you, okay, this is where your skeleton starts. And then in between, you can still have markers, but their lengths can be cannot be as long as this. So you're sort of like marking the beginning of a skeleton and the end of a skeleton by putting a lot of the markers. And x's correspond to the probability, so to the components that are to the components of the probability vector that contribute less. Then you use combinatorics. Let me write it here. using this Shannon-Macmillan-Riemann theorem and combinatorics in particular, more specifically, rather, you're using a version of the marriage lemma to match filars. And then you do, you sort of like start stitching these two systems one step at a time, essentially. You're taking longer and longer skeletons that are compatible with each other. And on each skeleton, you're sort of like either going from here to there or from here to there. Essentially, there is a joining here that tells you how to do it. And let me just try that. The fourth step is that using this joining, you're doing sort of like, just like in the Riemann rearrangement theorem, you go sort of like over and under, over and under. That's essentially the idea. But this is the outline. Next time, I'm going to start with characterizations of Asch homeomorphisms in the context of Bernoulli shifts. And then we're going to start going more into detail. Any questions?
I suggest we give Rob up a round of applause before he asks questions.
Oh, yeah, thank you. Yeah, if you, yeah.
All right, in that
I guess
case,
not.
let's give Alp another round
Okay.
of applause.
Yeah, thank you for coming. Good.